Hey everybody, welcome to Texas, all right? Yeah, so my name's Fred Cravel. I'm Senior Director at Capital One, and this is my associate Ashutosh.
Hi, my name is Ashutosh Pandya. I'm a Senior Software Engineer with Capital One.
Yep. So we're out of the Texas office, so welcome to our home state. I hope you're enjoying this. Today I'm going to tell you a story about what we've been doing at Capital One. I'm going to go through a lot of things probably pretty quickly, but I'll be around afterwards to ask more questions. As opposed to maybe some of the theoretical things you're hearing at these conferences, I'm going to give you the real world application of how these things work in a production environment for a company that is turning over as many loans as we are. You may not know it, Capital One has auto loans, and we're actually the #1 auto lending bank in the United States. So this system isn't some sort of click-tail marketing type streaming thing. This is the heart of this business, the biggest auto lending business in the United States. So, I don't know, have any of you went out and tried to purchase a car lately? Yeah? And probably took a long time sitting there with the F&I guy, the finance guy, the sales guy. So what we're doing is we're trying to streamline this process. So if those guys are taking 2 hours, 3 hours to get you through the process, it's not my fault. These things we've made happen very quickly. So we're modernizing this auto lending process. So 24 hours a day, people are selecting cars, they're picking out, filing loan applications with us. We're scoring their credit, we're setting up terms for these people, and they may or may not accept the loan. So historically, this has been a very one operation at a time. I file a loan, I see what the terms are, I go back and forth with the bank and adjust those terms and try to get a better term. So what we do, this all sounds pretty simple, right? You know, nice little workflow, maybe some streams and things, but I'm going to get into it a little more. So I was basically asked when I came on board with Capital One, like, make this thing happen in 1 second. I said, yeah, this isn't too bad, right? We got to pull some credit, you know, we got to get from various credit bureaus your FICO scores and things like that. We have to run some analytical models, right? We have to actually calculate what your debt is and segment out your customer. And then we have to run policies, basically weigh, you know, how much you can finance versus what we scored you out on. And we have to pick that best term, those set of offers, and we give that to the customers. So that doesn't sound so bad. I can do that in about a second. But we really wanted to do more. We wanted to make this less of a one-shot through these things. We actually want to run thousands of these things in the background in parallel. So we're not just running one analytical model against one set of terms on your loan. We're running all the terms. We're running many models, and we're doing this thousands of times to try to pick out the best loan that's optimized for those customers and give them all the choices. So I'm going to get into this a little bit, and you can see we've used the full spectrum of reactive tools across the board. So our problem, right? We were on a third-party based decisioning system. So this was really open heart surgery for the business, right? This system did everything about decisioning, segmentation of customers, and basically all of the automated things that we do to give people a loan. So this was the giant credit risk for the company, and we knew we wanted to do this fast. We knew we had to do this thousands of times a second. We knew it was a 24/7 operation, And we have some big data use cases, and I'll get into some of those things later. So after looking at some various technologies, this was a couple of years ago, we picked Akka. So we did some POCs, we brought in Drools for some decision tables, we used Cassandra to store our intermediate operational data that the system would work with, and we launched all this in the cloud. By the way, did I mention Capital One's one of the only banks that are actually in a cloud? So good stuff going on. So we needed to track these things real time, have escalation paths, all the monitoring, auditing you would ever need. So what does a loan processing application look like, right? We know there's a bunch of preconditions we're going to check. At a minimum, you got to be 18 years old. But we're also going to check and make sure you're not default on other loans with Capital One. And we know you have sound finances. We're going to check all your bureaus. We're going to run these models. And then we're going to do some post conditions that take these models into effect. So when we were implementing this thing, we knew we had these sets of preconditions. We had these other sets of operations we had to do. And we knew they fairly flowed in this order. And we didn't know how many more of these things we were going to add to the system. So like any good architecture, we built a DSL around these types of things and expressed how we would kind of work this workflow through a JSON representation of this workflow. And we backed it all by actors. So the actors actually ran this workflow in this decisioning system. This was prior to Akka streams or any of the other streaming things that we had. But so in a nutshell, very, very high level here, this is a simplified view of a workflow and steps and how the actor system handle these things. So this is one part of an ecosystem that underwrites loans, but it operates with the rest of the ecosystem through a REST API. So this is the first actor in the system. The REST API, basically his job is just to facilitate this transaction, start it, and create the bounded context for this whole operation. Then we have other actors that are sitting there. They get a signal, here's a loan application, and they actually are going out and pulling your credit. So there's a lot of impedance mismatch with these credit bureaus. Some will respond really quick, some will take a second and a half, some will be 500 milliseconds. So we spun these out as actors because we knew these were going to arrive at different levels, different speeds, different rates for the credit data that we're going to pull from third parties. And we have a set of scoring actors. So these scoring actors are sitting there. They're running credit policy models. Have any modelers out in the crowd, AI, any of those things? So this is where we inject this stuff. So we run boosted trees, linear regression models. So this is the secret sauce is in these models for how the bank works. And then finally, we optimize out these sets of decisions so that, and we give you, various points, and we try to get the breakpoints for the APRs for the person that's looking at the loans. So when you're sitting there with that F&I guy from Capital One, he has all the data. So we can figure out, okay, do you want to put a little more cash down, or do you want to adjust your terms, have longer terms? We want to give everybody all of the information so they can make the best decisions. So why did we choose Akka? So we knew we were orchestrating many steps, and queuing and ordering these things was going to be critical. I mean, how many of you guys have written a thread executor pool? How many want to write that thing again? None of us, right? We don't want to have to do this. We don't want to, have to deal with the asynchronous nature of thread pools and things like that. This really, made it very easy to deal with these things. There's other data sources. We knew we'd be plugging in more bureaus and more things like this, so we wanted to encapsulate that type of So we knew we were going to run thousands of these executions. We knew we were going to maybe run a lot more. And so we wanted to distribute this load across many servers, many cores, and we fan out some of our operations, and I'll show you a little bit more about that. So unlike the proprietary DSL we were locked into before with third-party tools, we took our Java and Scala expertise and we were able to plug them into these frameworks. I've been asked a couple times, how much does the engineer need to know about Akka to do these things? Well, if you want to take one thing away from this, is you don't have to know a whole lot. We've wrapped some of these things in a DSL, and some of my engineers don't really even know they're writing actor code. So we've plugged in places in the code where these engineers can write just pure Java functional coding, POJOs and services. I'm going to show you a little bit about that. So we built this DSL, domain-specific language, and it's really just a JSON document that defines a message handler that gets invoked, and then a bunch of operations that happen as a result of that invocation. So I'll go through this a little bit more, but the system that runs this DSL parses the JSON and defines the ordering and sequencing of the execution. And then Spring Beans, we pull those into the actor. They implement an interface driven by the message, and that actor system is just simply sending the message into that bean. And then these beans then emit another message that then cascades onto additional steps in the workflow. So we can have these sets of things that run in parallel. We can have these things grouped together that run in sequence, and we run them one after another. So the workflow actor kicks off the whole thing. So we can run many of these workflows, but this is one example of how we look at it. We have these group handlers and a handler that overall kicks it off. But the group handler, his responsibility is a supervisor. So he supervises these groups of things that are getting executed. He runs them all, sits there and waits and collects them. And then he signals the next group actor to do his group of things. So we finally call this, and we either fan it out or we call these beans individually. But in this way, we can extract out the ordering, the number of things that are getting executed, and just how the overall workflow is structured outside of code. It might have been a little overkill, but it's served us well. So how do these things happen? It has 3 basic steps: what to do with a given message type, a reference to the bean that you want to execute, and finally, some little routing logic, some rules so we can do bypasses and jump over pieces of the whole workflow. So initially, we come in, drive an application into these workflow, and define keywords like current message that says what to do with what the previous output was. So we can direct the elements being these groups of things to run based on a specific message, or we can just say, give us the next message. It doesn't really matter. We put all these things into tuples so that we can easily pass these things around, and the beans, the actors themselves can unpack these tuples, or the beans that are running the messages can unpack the tuples and get what they need. So there's a conditional section in the DSL that looks at the class of the return message to detect errors or just simple matching logic. This example is from the pre-scoring step where we have an A for approved, and if we're not A, we want to do something else. We don't want to go out and pull your credit if you're 17 years old. We won't get much on you. So we have these conditional executions where we can bypass some of these things. And finally, a then condition. Detecting a rule then routes to some other execution in the workflow. So we can have the consequences of these things jump past, go to the end of a workflow, and finally, loop out of the overall execution if we need to. Now, you can write all these things with actors, telling actors, and those types of things. We just this is where we obfuscated this away from our engineers who are writing these beans. And this is why, a lot of our engineers don't know that they're even running these things in Akka in some cases. So this is the actual actor. A piece of the router code where we're calling a bean. So we have a couple things going on here. We have the concept of carrying over all the previous request messages. So if we're folding in applications with credit data and other things, we kind of pack them together. And then finally, this thing has already parsed all of the DSL. And he knows what the next sequential set of things to do are. This is a sequential actor finalizing the coordination of the next step to move on in our workflow. So you can see we've got a list of actors that we want to run through in this sequence, and we're just telling the next guy, here's our message, and report back to us, to the self, when we are done with whatever set of coordinations you're doing. So we kind of have this hierarchy of coordinators to manage this transaction. And here's the actor, right? Or actually the bean that the actor is calling. So we have a simple implementation of a service interface that takes tuples and outputs tuples, and this particular example has a bunch of Spring things auto-wired, and run some credit risk and some tables and pulling out data. So this is what our developers develop. So they're not all worried about telling and fanning out and those types of things. We kind of bundled that together in one place. So all the business logic is encapsulated in these types of things, all driven by that DSL. So when you unfurl this gnarly set of things, this is still a simplified version, but we can have these different paths, different outs, where we'll get declined and jump straight to the end. But overall, we're carrying through, applications and credit reports and those scores from those credit reports, and then we're doing some segmentation, pulling the details of the customer, tiering them up. People with good credit is top tier and bad credit bottom tier, and figuring out what products we're going to select for them. And it looks very linear here, but a lot of these things are done literally hundreds of times as we're executing. So we'll actually do multiple product segmentations so that we have different areas of the nation, and we let people actually shop nationwide. So I'm part of Consumer Auto. We actually do the front face of basically nationwide auto sales. So we don't have a particular location, but we segment out all the areas. So this is a JMeter graph. This is just on a small laptop. 486 applications a minute. This was nominal speed on a small laptop. When we scale this out to things on Amazon with compute clusters and things like that, we get a lot of benefit. The point I want to make here is on our previous legacy systems, that was somewhere around 100 applications a minute. So 4x, smaller system. Another graph. So CB is credit bureaus. Save is actually writing to an Oracle database, and the time is in milliseconds across the left. The thin red line is actually where we're doing the most of the work, right? So this is where we're running the models and these things. I kind of brought this up just to show you the disparity in times you'll get as you're going through either doing these things, and why you need to like have these asynchronous actors to pick up these workloads and not just try to run these things all online, because they'll happen at different times, different speeds. But the benefit of the actor system I've seen is we can handle all these things asynchronously. They're not trying to poll or wait on these individual tasks or parts of the task. So saving, we actually do that asynchronously. You don't even see that as a customer. We try to stay in that 200, 2,000 or 1,000 range. That's where we give back you the answer. So we have the credit bureaus, our long pole in this situation. Gotta get credit. You gotta know what your FICO score is. But after that happens, after we do all the scores, all the thousands of iterations of scores and models, we give you back the answer right away, and then asynchronously save off a bunch of data for legacy systems to read out of Oracle databases. So that was our fast data use case. I'm going to tell you a little bit about our big data use case. So delivery of decisions near real time, pretty awesome, right? We gave the best solutions for loans, and people were happy. They had good visibility into all the options. But that's not good enough, right? We want everyone in the United States to wake up in the morning and go be able to search out cars across the United States. All the cars, all the prices, sorted by lowest monthly payment for you. Individually, each person has a different price for an APR, of course, right? So we have this use case where we want to search out and do book values across the nation. We actually run other analytical models against the vehicle collateral, against your credit versus the collateral, and choose in or out of policy and give you some sort of APR. And then sort all this stuff by monthly payment, colors, whatever. So the next challenge was make this run in under a second, right? We have 3.5 million vehicles in inventory at any given time. So run analytical models against 3.5 million vehicles and make it individualized for you and publish it to a website. So here's a shameless plug for our product, Auto Navigator.
Looking for a new car?
Yeah, I'm on Capital One's Auto Navigator site. It lets me find and finance a car all in one place.
Nice.
Yeah, I can check if we pre-qualify for financing without affecting our credit scores. And see our rate and monthly payment on each car.
Oh, that makes it easy. Whoa.
Capital One's Auto Navigator site. Find and finance your car all in one place.
Probably should have done that outside.
Yeah.
What's in your wallet?
Yeah, so what is in your wallet? All right. So what was the problem, right? We had millions of cars. We had existing tech stacks that were built with legacy systems, some of them proprietary third-party software. And we wanted to do things like rate comparisons and those types of things. The existing technology just didn't do it. So what did we do? We simplified some of the execution so that we can make this work a little bit better. And we pre-computed a lot. So book values and those types of things. We did a big data project to basically, we're computing book values on cars. We worked with KBB and NADA to improve their algorithms on how they do book values. And we co-located the compute layers with the data. So, and we co-located our teams. So we're all in Plano, Texas, and we all got in one space, and we hashed this thing out. So we brought all the experts together, and you can see when we were doing this thing threaded, right? If we had to go and try to calculate payments for everything, we were taking like 50 hours, and nobody's going to wait 50 hours. It would be like, I logged into the website, and tomorrow we'll tell you what the price of all the cars are. That's not going to work. So with reactive systems, we cut this down under a second. We were able to squeeze out every last ounce of computing power to do all these scores. and to give you, basically what it shows on the right is, sort by monthly payment. No one else in the industry does this. Dealer Navigator. So this is our dealer side. So we actually have like a three-sided marketplace here. We have dealers, we have you as a consumer, and we have lenders, us as a bank. So dealers can go into this tool. They can see all the options for terms and warranty and down payment, cash down. So what previously could have been a really horrible customer experience is now the new norm. All right? Give you all the prices, give you all the options, put all the details out there. We really like to do what's right for the customer, and our customer experiences are driven by those types of things, and that's where this technology came out of. So it used to be a one vehicle at a time selection. This guy on the left had to punch in this form, hit recalculate, hope he got an answer he wanted, do it again, recalculate. Now we score out the whole dealer's lot for this person. So you can see all the cars this guy has qualified. We're starting to add machine learning, AI recommendations for the customers in this equation. So these technologies have really unlocked a big amount of features and functionality. So this is how we did it. So it's what we call a fan-out pattern. So much like the supervisor I showed you before, we have some sort of inventory selector that's generally set by the customer. I want blue Hondas and 700 miles radius from my zip code, crazy things like that. And we pull out of an in-memory database that we built from the inventory we have for nationwide, 3.5 million vehicles. And we fan these things out to either a set of actors that are generating deals and trying to find the best deals for individual vehicles, or we fan this out to a set of actors that are just validating the policy across all of the vehicles. So as we do this, we are federating out all of these decision points and these models, and then we collect this back in memory and build facets out of it for sorting and paging against this. So actors to actors, in memory, a lot of these things happens very quickly. So this was a non-reactive system. This was the one that would have took us 55 hours. So you can see we tried a couple different things. We tried using threading connection pools. We tried no connection pools. And we got a little bit of a benefit, but we were trying to hit that 1 second mark, the very bottom line. Wasn't going to happen, not with this particular technology. So with the reactive systems, this is one server. We're getting, it's not quite linear, up to 16 or so simultaneous users, but we federate this over 2 or 3 servers, and we can handle the load. Keep in mind, each one of these transactions, 180 milliseconds, 200 milliseconds, so we rip through them really, really quickly. So this is what services that Auto Navigator website. We are able to, pull through and get enough throughput on 3 relatively big systems, all we need to score out and run through inventory in the nation. So had to throw some plugs in here for Cassandra. I'll let Ashutosh tell you about what we do here in the code.
So we had a use case where we had to use Cassandra as our data store. And the source code that you see over here is no different from what we used to do with our SQL database. So the configuration, this is the Cassandra configuration where we create the Cassandra factory bin, and using the cluster. The first thing that we are doing is creating a cluster, providing all the endpoints where the Cassandra is running, up and running. And once we have that, we create a factory out of it. A few things that I would like to bring point over here is we are using Spring data over here. So probably the next slide would give more reports. Yes. The good thing about the Spring data is all you have to do is create an interface and extend the Cassandra repository. Now, it is not just limited to Cassandra, it is applicable across all the database. Oracle, SQL, NoSQL, all the database, we can rely on Spring data, and they have the individual implementation based on the database. So over here, the moment we extend Cassandra repository, by default, it gives us the CRUD operations, read, write, update, and delete. The other good feature is we can define our own methods. One more prior to that. All we have to do is create an interface. There is no implementation for this. So if you look at this particular method, find by borrower first name, what does that mean is we are, if you want, the moment we use this particular method, all we have to do is send the first name for which we have to fetch the data. We don't have to explicitly implement this particular method. What does that mean is we have an object which is of name person random int, which has a field called borrower first name as one of the parameter, and which represents the column of person random int table. So that's the ideal random repository, and the code beneath that shows how we create a service and auto-wire the ideal repository and use different methods. Like if you want to delete all we have to do is repository.delete all. There is no implementation as such, or there is no method defined in the interface itself. It comes out of the box the moment we extend Cassandra repository. So,
the Cassandra has been really good for us, being high-speed reads and writes. Of course, you have to be careful with Cassandra. It's not SQL, it's not transactional. So, but being able to spread this across the entire compute cluster of Cassandra and have some of our operational data. This one's basically we assign you random numbers to people when they come into the application so that we can do different tests with you. So we have little bits of data that we'll store off about people, and when you come back again, we give you the same set of random numbers so that we give you the same treatment over and over again. We're not putting you in different tests and confusing you as you buy cars from different dealerships. So now we have these highly performant systems that can generate tons of data, but we need to be flexible and, no pun intended, react to the market. So we got to react. The business tells me, hey, we need to rapidly deploy these models, all right? I want to do this twice a week, 3-4 times a week. So what we're doing here is we basically are taking a bunch of data, we're dumping it into analytical systems, big data systems, and we're basically refitting these things. We're figuring out what to adjust, what pieces of the market to avoid, who to avoid, what types of things will be more profitable for Capital One. So how do we do this? We actually put multiple machine learning models in production. We run simultaneously up to 20 different models at one time. So the system actually pulls these from S3 buckets, and we have a rolling set of these things. And we have some guardrails that we leverage just so that we know the new models aren't going off, and we can back off to an N-1 version of these types of models. So the system can easily delegate and control these different models, and the data scientists, they're taking data out of the lake that the system put in the lake to build these models and then retrofit them back into the system. So this really isn't about Akka, but it does, having Akka and having so much compute power on tap really lets us run these things simultaneously and save off the data as needed. So inside of our decisioning system, by the way, I never told you what IDEAL stands for. Intelligent Decisioning System, Intelligent Decisioning Engine for Application and Loan Processing. So This system has two different types of audits it does to Kafka. So we have basic audit points, because we have to go back like 7 years sometimes. Just if an auditor says, what happened to this guy 7 years ago? Why did you decline him? We have to be able to go and reconstruct what the model did and what our decisions were and why the code made that particular decision. So we stream off intermediate audits of different points, different functions. All of the actor output gets streamed out. And we have credit. We stream out the credit as well. So we put these into edge nodes in the lake, and we have a process to go through and validate and classify, and then we even bring them off to offline systems. So we stage this stuff out here, and this is what we use as the basis for building analytical models. So event sourcing is what we're doing here. Kafka plays a big part, and you know. So it's some more pseudocode. Go.
Yeah. So this is the Kafka's pseudocode where we actually initialize the Kafka producer, where we want to have a connectivity to the Kafka cluster, and we want to send messages to that particular Kafka cluster. It is pretty much straightforward. We are getting all the bootstrap server properties, or what kind of key serializer we have to use, what kind of value serializer we would be using in order to process these Kafka messages. So the first thing over here, one of the things that we are doing is we are initializing the Kafka topic, and we are initializing the Kafka producer. Once this is done, your Kafka producer is ready to use. Now here, this is the place where we are actually pushing the events to the Kafka server. And the way we are doing over here is we are using this particular API called send message, send method, and in that we are passing the record that we want to push it to the Kafka, and at the same time we are also making sure that we implement the callback mechanism. What does that mean? Is we are making sure that it is 100% delivery. If there is any error, we log that particular error and we persist that particular data in the Cassandra, so that at the end of the day, if you want to run a batch process on that table, we can do that, and either we analyze it or we can again post back to the same queue to send it across to the Kafka server. This is about Kafka Post mechanism, like sending the messages to the Kafka server.
Yeah, when those auditors call you 7 years later, they don't want to hear I had a network connection problem. So we got to store this data off into Cassandra if we can't get to Kafka. I think you'd probably see this as a typical event logging pattern, where we're event logging some of these things to the database and coming back and pilfering through them later and pushing them back into the pipeline.
Yeah. So when now for the consumer part, the way we are consuming this particular messages are we are using the Spring Cloud Stream over here. And the good part of Spring Cloud Stream is it follows the same methodology that our previous speakers mentioned about the Akka streams. It has 3 components. One is source, another is transformer, and the last one is the sink. Source is the one which is responsible for reading the messages from the Kafka. So that reads the message. Once it reads the message, we transform it. And what does that mean is we apply the business logic on top of the message that we have received. And once we have massaged that data, we give it to the sink. The responsibility of the sink is either you store it into another database, or you push it to another Kafka topic, or you just log it as for this particular code. What we are doing is we are using log sync. What does that mean? Is we are just logging the data that we have received this particular data in this format. So one other use case of the sync was how we are using, say we end up in a failure, we end up in scenario where we face some failure. So we take that message, process it, and put it to the failure stream. meaning we push it to the another Kafka topic, which is more of like a failure topic, which takes that, and there would be another stream which will read that message from the failure topic, process it, and retries it. So yeah, this is about the consuming part of how we consume the message and process the data. Fred?
Yeah, so once we have all the juicy data in a lake, right, we actually took some of those same beans, some of the same pojos, and wrote a Spark program out of it. So now we have the last couple of years worth of data, last couple of years worth of credit history for people. We can put in new credit data if we like. And we gave our data analysts tools. So after we repackaged these decisioning components, these tools allow them to basically first drop in some set of models, drop in some set of policy changes into S3 buckets, and the system to run that said decisioning system as a historical set of runs. We affectionately call this the matrix because we were able to time shift and go back and forth in what we do. So previously, we would have had our data analyst going and writing another SAS program or writing another tool and re-implementing basically what was already our production decisioning system. So now that we have these things modernized, Java, Pojos, we can run these in Spark context. These guys are literally running, you know, the last year's worth of applications through the new adjusted credit policies in minutes. And they're not writing SAS. They're more worried about the credit policies, how models slope, and all those good things that our data scientists like to do. So that's really about it. I think we have 10 minutes where we could take questions if anybody has some.
Hello.
Yeah. Hi.
How long did it take for you guys to build this, the first version?
So parts of it were built, so the fast data part, we built that in about 6 months. And then the big data, the scoring for the cars, you know, and sorting of those things, that was another 3 months effort after that. And really the long pole in all of these things is the open heart surgery we're doing on the business, and we're in a highly regulated business, so there's a lot of credit risk, and we had to implement slowly, test, evaluate, implement a little bit more, test, evaluate, and ramp it up until we were 100% of the nation. So.
Question on the testing strategy.
Yes.
At a high level, you guys have some 50,000 test cases or auto tests, and how do you like distribute like auto tests or manual tests and overall? Thanks.
So it's an interesting question, especially when you start dealing with data analysts and data scientists. They want to run like, say, let's just run the last year's worth of things and see how that worked. So we did those types of tests. But as I explained to these guys, the random-based testing is random results in production. So we balanced that with the ATDD, automated test-driven development type scripts. Since everything was, you know, kicked off through RESTful APIs or streams, we just load up those things. We write either custom kind of testing harnesses to load up these things, or we run test automation through things like Gherkin and Cucumber for specific test cases. But we were looking at historical performance of these things and the performance of the new thing, and comparing, you know, did everybody get the same APR they used to get? Did they get the, you know, same treatment that they always got before? And you would think a credit application, you know, name, address, phone number, date of birth, and, you know, an APR. Well, there's a lot more that comes out of these things. All the segmentation information. There's about 200 variables that come out as a result of the decisioning process that we had to test across every type of credit policy, every type of person, and every type of condition that we would encounter, both good and bad. Yeah.
I have two questions.
Yeah.
One is, maybe I missed it, but was there any benchmarking, and how much data we're talking about?
Benchmarking of which?
End-to-end performance and...
Yeah, there was the slide I showed with some JMeter.
Sorry if I missed it, I was late.
Yeah. So, I mean, before we were running on some legacy systems, and we basically got to a point where we could quadruple or quintuple our business, in which case we said, I don't think we're going to like double or triple the amount of cars that are getting sold in the United States, anytime soon. So that was good enough for us to be able to do those
But nothing
things.
in terms of TPS or something, like how much?
So I showed on a nominal, small, like just a notebook. We actually measure these things in minutes, but around 500 applications a minute. So if you can imagine scaling that out to 2 or 3 servers, now you're talking 1,500 or so applications a minute, 24 hours a day. That's a lot of people buying cars.
And what was your criteria for going with Cassandra?
I'm an old Cassandra hack, I guess. I'd used it previously, and one of the other graphs I showed, we have like the same amount of data going into Cassandra. Is taking literally 80 milliseconds, going into relational type systems, Oracle, highly performant Oracle, it was 8 or 9 seconds.
I mean, Cassandra is kind of NoSQL, column oriented.
Yes.
I mean, is the nature of the data model fit?
Yeah. So I mean,
With
we
Cassandra?
use columns, column families for our data
But
models.
is that how you were retrieving the data from Cassandra?
Yeah, so you can build out column-based, basically column families that looks like a relational record with keys and all the good things you would
But
expect.
underlyingly, it's not really relational. It just allows to go to different collections and get the data. It might
Very
not be
correct. So, I mean, you have to plan out your query patterns, your strategy for how you're going to query the data ahead of time when you build these types of databases. You have to also plan for concurrency, how you're going to handle any kind of locking or those types of things. Generally, you do more of a journaling type of situation where it's not a fully consolidated state you're writing, but it's some set of number of records that you're reading through to build that state.
Okay.
So.
And how mission critical was the data? Because like Kafka is not very suitable for mission critical because of the way it's ruled.
So this runs the biggest auto lending industry, or we're the biggest lender of auto loans in banking. So number one. So it is very mission critical. So that's another reason Cassandra is nice. We have multiple copies of the data. We have cross data center replication, and we use it as a backup for Kafka.
Okay.
So if our messages can't get into Kafka, or that cluster's down, or I have a network partition where I can't read it, I write that back into Cassandra and let that replicate it, and then we pick that up and push it back into Kafka again. So we have multiple relief valves for failures.
Thank you very much.
Mm-hmm.
Oh, that was good talk. Thank you.
Thank you.
That was good. So I have a question on your one slide. I have seen your architectural diagram for ideal. What do you call that?
Ideal. Yeah.
So there is an Akka-based streaming component that actually feeds into Cassandra, and then also feeds into Kafka topics, right? So what was the architectural? I mean, can you give us?
So
kind of an
Ashutosh
idea?
went through that piece of the producer code, right?
What
So-
was the basis? I mean, is Akka really necessary there, or is that?
No,
You can actually
this
scale your
was,
Kafka
so I'm
instance.
trying to tie it. We use like all of these things.
Okay.
You know, the reactive part of it, this wasn't really Akka. This was more the streams-based solution on how we'll do event sourcing from these systems. At two different reasons. One is the audits I spoke about. They can come back to us 7 years later. And the other is just for the machine learning so that we can build up models off of this data. So it's an event sourcing for all of these systems and the audits.
I think basically this event log, event sourcing is actually the
Yeah,
key need for your auditing reasons, right?
Yep, so we event source out different audit checkpoints and model results, and then we also siphon off the credit data to the lake so we can build other models and do performance of our models in
Yeah,
that
basically,
system.
technically, I don't see the need for, really for the scaling purposes, Kafka can scale itself as a cluster feeding into your Cassandra, but I think what you said, that's
Yeah,
what I
but
see
both
the
of them
need is.
are really good at those aspects, being able to add more and have the shards just, replicate across those and rebalance itself. They both work really well.
Great, thank you.
All right. Well, thank you, everybody, for sticking with me. I'll be around. I'll come back to the back if you have some more questions. But thank you.